Hello everybody, Lord Root here, and today I thought I would do a tutorial on how to get into space. This is mostly meant for beginners, however, with the new atmosphere, some people may be struggling to get into space, so I'm just going to start a new sandbox game, and I'll call it tutorial. Now, one of the things that's worth mentioning here is that, first of all, there are a lot of options for you to select from here. We did select Sandbox, and that's one of them compared to Career and Science mode. We can also pick a flag. I'm going to go with OMB on that one. But the idea is that Sandbox basically gives you everything at once, and it's your job to sort of figure out how to fly the rockets to get them to where you want them to go. There's Science mode, which adds in the caveat that you have to unlock your technologies, but in that case you don't have to worry about funding, and you can at that point do things like basically you unlock the parts in whatever sequence you think is necessary, and you take that and you try to progress. And then there's Career mode, which is basically you have funds and you have reputation as well, and that's probably the hardest mode to play, but there's other options. We have these difficulty options here, even on the Sandbox mode now, and we can set the game however we want it to. So for instance, we can do Easy mode, which you might like. We can even make it easier by allowing ourselves to automatically hire crew members to fly a vessel. And we can move these sliders over here to get a sort of custom deal going on. I'm going to go with normal though, because normal I think is what most people are going to play, unless you are really, really nervous about playing. So after this loads, what will happen is Gene Kerman will come up, and I'm going to move out of that because I've been playing for a long time, and I'm sure Gene's advice is worthwhile, but I am not really, in need of it. I've been playing for such a long time that it's just not necessary. And so let's work on a rocket. Every rocket needs a command pod of some kind. It needs some kind of controller. So you can either use a command pod like this. This sort of resembles the Mercury capsule. Or you could use a probe. And a probe is sort of robotic. However, I think it's cool to get people in space. So we're going to do that. We'll leave the probe for another time. Probably later during this tutorial. We also want a way for us to decouple from the rocket whenever it's spent. And we can actually do a number of things here. We can do staging, for instance. And so what I'm going to do is I'm going to grab a solid rocket motor from here. And solid rocket motors have some interesting properties to them. For instance, you can't throttle them, although before you get out onto the pad you can set their thrust. You just can't change it once you've gone out to the launch pad. So we'll do this guy, and we will also do this as well. Let me just find the very large rocket booster. This is also a solid rocket booster here. And the idea behind staging will become important in a moment once I show you, first of all, how to tell whether or not we can even get off the pad. So Kerbin has gravity. By the way, I think I should explain before I go into that I think I went a little bit fast here. In order to attach parts, you grab the part you want to attach, and then you see that little green ball there? There's probably a green ball down here, and you just match them up and click. If you want to delete a part, you can either click on and hit delete, or you can drag it over to the side here. Okay, at any rate, carbon has gravity, and that's not such a bad thing. I mean, you definitely do want things to sort of stay in place. And so, what we need to do is we need to first of all figure out, is this thing going to be able to get off the launch pad? You'll see that we have vessel mass here. And our vessel mass is 27.2 tons. If we go over to our large rocket motor, then this has a thrust of 599.4 kilonewtons. Now you'll notice there's actually two thrust values here. There's one which is ASL, that is not age, sex, location, for those of you who have been on AOL Instant Messenger. If it even exists anymore, I'm not sure. But there's also the vacuum as well. ASL is the thrust at sea level. And as the atmosphere gets thinner, usually what ends up happening is that you get a little bit more thrust out of this, at the cost usually of something called ISP. If you right click on that, where ISP's actually gone up, the ISP is essentially a measure of efficiency. So these solids do not have very good ISP. Usually an excellent value is somewhere maybe, or a normal value for space is around 300 or so seconds. And when I talk about delta V, that'll become important. But at any rate, you know, this deal here is that there are engines that far exceed that. For instance, this nuclear motor that we're not going to use today has an ISP of 800, but only one of 185 on the ground. Its thrust is also pretty weak to boot. And then if we tab over here, maybe, I'm trying to find it, there is an ion engine. This is it up here, and it has an ISP of over 4,000 seconds. So high ISP is good, but the higher ISP engines you usually pay for with lower thrust, and vice versa. So, let's get this thing going. We want to calculate the thrust-to-weight ratio. And we know that on this first stage we have about 600 or so kilonewtons of thrust. And we have 27.2 tons. Now, it is important, I believe, to point out that this is not a measure of weight. Mass and weight are two entirely separate yet related things. Mass is sort of your resistance to force. It's what gives you, it resists your change in inertia. And, pardon me. And as far as, your weight is a force that is, the mass divided by, or the mass times the acceleration of gravity, which is 9.81 on carbon. However, as a quick rule of thumb, 10 will do it. So, the amount of weight we have is 270 or so tons, 272 tons force, let's say. And the amount of thrust we have is 600, we'll get a little bit over 2 times gravity pushing up on the rocket. That's our thrust-to-weight ratio. You can also calculate it by taking your thrust and dividing that by 10, and then dividing your weight into that, or your mass rather. So let's see what happens with the rocket as it becomes deprived of fuel. If we move this slider over, you'll see that we have the center of mass. It starts out here in the center, and as we burn off fuel, we lose mass. You see, rockets work off of Newton's third law, that for every action, there's an opposite and equal reaction. And so the force that we push our propellant out is the force that's applied to this rocket. If we drain this thing of fuel, what will happen is it will go down to 8 tons, and that is quite a bit. And that's enough for us to push this stage up here to a fairly large height. Now when we stage this, we will have another deal going on. If we take this hammer, it has a thrust. We're going to go with the vacuum because that's about where it'll be by the time this stage is decoupled. But, you know, we're going to take this thrust here of, we'll say about 230. And at this point, we're at 3 tons. So, you know, long story short, we can get a thrust-to-weight ratio out of this of about 5 or so. Now, let's talk about stability some, because gravity is pulling on your rocket, and minor oscillations in your rocket will cause it to tip over. And so what you want to do is you want to put fins on this. Now, whether or not you want to do fins on all rockets is debatable. There are some that just don't benefit from it, but if you hit the X key like this, some parts you can attach to the side, and by hitting the X key, or you can just click on this guy here, you're able to place those parts symmetrically. So, one other thing we want before we go, it would be nice for us to have a parachute, because the occupant is probably not going to like crashing down to the surface whenever he or she re-enters. And it is proper to say he or she at this point, because we have female Kerbals now. Right now we have Jeb manning the capsule here. And he is a pilot. A pilot is able to use stability assist and other things. They can, for instance, point in certain directions automatically. Bill is an engineer, which means that he can fix broken parts, certain broken parts, mind you. He can also repack chutes. So, let's say you land on Duna, which is kind of like Mars in this game. Well then, you can use your parachutes to help you get down, and then Bill can get out and repack them. And then you don't have to worry about carrying extra parachutes. Meanwhile, Bob is a scientist, which means that you get bonuses to science. In some experiments, they have the issue to where once you use them, they can't be reset. Right now, Bob is kind of along for the ride, because science isn't all that useful in sandbox mode. But, we'll take this. And we'll just go with that. Now you'll notice I have a couple of mods down here. This is Kerbal Engineer. We can do lots of these calculations with it. So if I click on this, you'll see that my thrust-to-weight ratio is 2.5 on this stage, which is quite nice, although that's probably looking at the vacuum thrust-to-weight ratio. And we have this measure called delta V that I'll talk about, and I'll talk about how to calculate that. For now, I don't want to really do too much with the mods if you're a new player. But one more thing before we go, I want to discuss why we're putting fins on this rocket. You see, if we click here on the center of mass, we get our pivot point for the rocket. And if we click on this wing down here, we get the center of lift measure. And basically what's going to happen is that as we move through the air, these fins will push against the rocket. And we have 4 of them, so they're going to push against each other equally. And this will keep the rocket going in a stable trajectory. And so the idea is that as fuel drains, with some rocket designs, because you have the engines not losing any mass, this guy will actually move down. And so what you might care to do, and what you probably want to do anyhow, is take the offset tool here, click on the fins, and move them down so that you can get a little bit more maneuverability out of your rocket. Well, let's launch this. I'm not going to save it by any means. Those of you who know a bit about orbital mechanics might have an idea what will happen with this rocket, but let's test an interesting hypothesis. And let's see if the sort of common sense idea that having the rocket point straight up to get into space will get you into orbit. Now, we don't have any throttle on this, so we can do 2 things. First of all, I'm going to hit T to help assist in our stability, and I am also going to hit space to launch. And you can see we're taking off now. And this rocket should get us pretty high up. It'll keep us going for a while. You might think that we'll certainly get into orbit with this because, well, for one, the rocket's big, right? And big has to mean powerful. So you can see we're quickly picking up speed here. In fact, we're almost within maybe 100 meters per second. If you look down at this navigation ball here, we just hit Mach 1 or so, and you can see we have Mach effects coming. Now if we hit M for the map, we can fly it from this view too, and sometimes it's good to do so. But you can see we are getting, I suppose, the shockwave going on this, and something interesting is going to happen. You can see that shockwave is turning red. That is because the vessel is beginning to heat up. What's basically happened here is that there's air in the way, and it can't get out of the way, so it gets compressed and it heats up. That's something called shock heating. Now, if we hit F11, we will get a visualization of this. You can see this red part isn't heating up too much, but this engine, because it's lit, is slowly heating up. You'll also notice this bar is coming up. Well, that stage is about spent, so I am going to hit space, and I'm just going to launch. Let's go back to the map. You can see we're getting pretty high up into orbit here. And we can keep on going like this for a very, very long time. But eventually, we just have this very steep ballistic trajectory. And so one thing to note about this is that if you remember learning about conic sections in geometry, a lot of your orbital paths are conic sections. This is a parabola. In fact, it's actually an ellipse, but because of the fact that the other end of the ellipse is in the ground, then that's not going to help us much. You know, we're going to hit the ground as a result. So this is a parabola that we have here. If you go at escape velocity, you don't get an ellipse at all. You get a hyperbola, and that means you're escaping the system. Well, while we're here, we can do a number of things. We don't have to take science, and we won't get any for it, but we can do crew reports, and we can even step out of the vessel here and fly around. I might leave that for another time. You can see Jeb is pleased as punch here. If you look down in the corner, and he is, he is very happy with it. In fact, it takes a lot to make him unhappy. He has a special attribute called the badass flag. And so we can speed things along because it's going to take 16 minutes to get here, and I'd rather not wait through 16 minutes. And if you can hit up here, like so, to give you time warp. You can hit the greater than or less than symbol. That'll work as well. Or another option that just recently came through is you can hit warp to here, and it will bring you down, or bring you over there like so, as fast as it can. There are limits on time warp that you should be aware of. Anyway, one thing that's worth noting is that the further you get out, the slower your orbital velocity becomes. I'm just going to warp here, and we can watch the speed pick up. Now, there's no real point to, I suppose, to keeping the stage, so we're just going to let it go. But we're coming in at quite a steep trajectory. Let's see how fast we get. Ideally, you want to be facing retrograde, which means opposite of the direction that you're currently traveling, and you can do that by either doing it manually, or there's a button over here with pilots. Sometimes it works and sometimes it doesn't. In this case, it's gotten confused, probably because of the steep trajectory that we've taken. Let's time warp through this. When you hit the atmosphere at 70 kilometers, that's the boundary for space, then time warp will stop, and you have physical time warp, which means that it's trying to do some of the calculations there. If we do our visualization now, you see our capsule is heating up very, very quickly. This is not such a good thing for Job. If this thing had been going somewhat faster, then it would have been a problem. Well, I'm going to pop the parachutes real quick to slow us down. And Job is on the verge of just surviving that fall. But, yeah, that didn't get us to space, did it? We can just go like this. Let's maybe see how we could get to space instead. And because, it's problematic. You'll see, we've got this mission report here. And I'm going to go for a different design here. The design in particular that I'm going for is going to be one in which Jeb can get into orbit using this multi-stage design. So I'll take one of these small fuel tanks right here, and I'm going to attach an LV-909 to it. Now the LV-909 is designed for being up in space. In fact, look at its ISP. It goes from 85 to 345 very quickly, and we can do that. The structural tab again has our decoupler, and now it is a matter of us developing a stage that will get us up into orbit. Now, when you're in career mode, you have to keep in mind first of all, what's available to you and what's the cost. And something too, this guy here is the longest tank you can get for liquid fuel. This guy is half that, a quarter, and an eighth. Now you start out with none of these. You only get solid rocket boosters in career mode, but you're able to work your way up eventually. So what we can do now is we can throw on a liquid fuel engine, and that will cause us to move a little bit forward. We have two options here that are appealing to us. We have the Reliant, which has slightly better thrust and slightly better ISP. And actually this guy has a little bit better ISP than the other one, but it's worse at sea level. But the other thing about it is it has engine gimbaling, which means that the engine can move around. Now, again, if we look at this, we have about 4,500 delta V. If you do the delta V calculation, then that is enough to get into orbit. Or it's not enough to get, or that amount of delta V is actually more than enough. With the new atmosphere, you need 3,500, and the way you calculate that is kind of similar to the way you calculate your thrust-to-weight ratio. So what you do there is you take your ISP, and first of all, we need our masses. We need two masses, in fact. We need the mass of the full rocket, and then we need the mass as well of the empty rocket. So we have 5.2 over 5.2 over or 9.2 over 5.2. Take the natural logarithm of this, and so that ratio is about 2, which means that our for this stage at least, that our delta V, or our thrust to weight ratio, being 2, that means the natural logarithm is a little bit shy of 1 here. What you do now is you take your ISP here, and at the ground that's 270. You multiply that by the acceleration due to gravity, and that'll give you something called exhaust velocity. So in that case, we have about 2,700 or so on this stage, and with a thrust-to-weight ratio near 1, we should have something kind of close to that. I'll bring up Kerbal Engineer to check that. We have about 18,000 or so. Now that is really interesting here. We went, oh, I know why, because our fuel. We need to put more fuel in this thing. In fact, we forgot to drain the fuel out of this, didn't we? No, it was correct. And actually that was 13.2, so as it turns out then, it's actually 3 times that, it's 3 times that 2700 or so, or thereabout. No, it's not that. It's not that at all. It's actually closer to 1. So yeah, that's what that is there. A little bit more than 1. We can do a similar calculation with the top stage if we want to, but it depends on what kind of player you are, really. Now, of course, we need fins as well. I'm just going to sort this by cost. I'm going to get these cheap fins here, and I'm just going to put 4 times symmetry on them. Let's see what happens when this guy runs out of fuel. The top will run out first, as will the bottom, so it's important in this case to have a low, I suppose, center of lift would be the best way to do it. Let's get these guys down just a little bit further. You can actually get these with the offset tool. You can get those things off the rocket. And let's just calculate our thrust-to-weight ratio real quick. Our thrust-to-weight ratio is, with this guy, it's going to be somewhere around maybe 1.2 or so. 1.25. Is that accurate? Let's see. 1.5. Well, let's do that. Kerbal Engineer is a very good mod to have. It takes a lot of the calculation out of it if you just kind of like to play by the seat of your pants. Now Jeb here can, you know, he can do a number of things, but we're going to turn on stability control because now we can deal with that more easily. And I'm going to hit caps lock here, and if you hit control you'll throttle down, shift throttles up, and then Z throttles up all the way. So we want fine control because what we're going to do here is we're going to do a gravity turn. And so let's get that going. We're going to pitch over to about 85 degrees at 50 meters per second or so. And by the way I'm moving this rocket around is with WA, S and D, and then Q and E rotates it. Also, kind of important to note that at least here, that I'm gonna hit T real quick to turn this off. You can see now that my rocket is just sort of turning over naturally. There's some weird idea from the past, I suppose past versions of the game where the atmosphere is much thicker and you had to go up to 10 kilometers per second and then start pitching over here. They called that a gravity turn, but it's not. It's something called a pitch program. Now we want to pitch over gradually like this because what we're basically trying to do is we're trying to defeat gravity as easily as we can. And we can look at this guy here, and he will, he's just pitching over on his own. Gravity is pulling down the nose. It's nice to get to about 45 degrees or so as soon as maybe 10 kilometers. That is ideal for this atmosphere. You can see we're picking up speed. These guys are beginning to overheat, but they're about to get thrown away because our rocket's overheating. And I'm just going to hit F10 because those guys are known to cause memory leaks. So we need to point to the horizon here, and I'm going to hit the map mode. We have an apoapsis, and we just ran out of fuel. We want to get pretty high, and in fact, I need to be pointing down here. This direction is called radial that I'm pointing. That increases your periapsis. The apoapsis is the highest point of your orbit. The periapsis is the opposite point. It's the lowest point, but it is in the ground. So you can see we kind of sort of have an orbit here. How much fuel do we have? We have about half of our fuel tank. So what I'm going to do is I'm going to create a maneuver node here. I do this out of habit. And what you're going to do is you're going to burn close to apoapsis. As close as you can get. Now, chances are we're in at an angle. We can figure out how much of an angle by setting the moon as a target. If you right click on it, it says we have 0.2 degrees of inclination. So relative to the moon, we form an angle of about 0.2 degrees or so. But that's a story for another time. If you hit caps lock again, you'll want to turn off fine control. And we have a 3-second burn coming up. You can see that here in the corner next to the nav ball. Oh, another thing too, you actually, whenever you're flying these things, watch the nav ball, not the rocket. The rocket is pretty, but watching the rocket will get you killed. Now you'll notice here it says we need to change our velocity by 97.1 meters per second. And that's what this burn will do. We're doing what's called a circularization burn, and we're warping to that maneuver. Now, a rule of thumb with this is because the engines do not turn on instantaneously, you want to burn about halfway. You want to begin your burn early, about half of the amount of time it takes. So I'm going to burn at about 1.5 seconds. You also want to be facing on this guy here. Now I got pretty close, but in this case, we're close enough. It is micromanaging that and very slowly bringing down our electric charge. So it may be a good idea just to use stability assist here. In fact, maybe fine controls in order. You want to be pointing as close to this guy as possible. And I almost missed my burn. There we go. We're like 1 meter per second off. We can go a little bit prograde now. And this is something called circularization, this process. But you can have a different deal here. For instance, you can burn out and it'll increase your orbit, or you can burn in. Maybe I'll do orbital maneuvers in another video, because it'll become important then. But for now, let's talk about how we might get back to the KSC. Well, there are really two things to contend with. First of all, the KSC has, or the Kerbin, the planet, has an atmosphere. So I'm going to click on our orbit and I'm going to add a maneuver. And you can see that whenever we do this, we'll have a new apoapsis. We can push this out. Luckily, apoapsis happens to be above where we want to shoot for, because we want to shoot a little bit to the east. And apoapsis is actually the best place to do it, because you have your least energy there. Likewise, if you're trying to increase your orbit, you want to burn at periapsis. But we want to bring this guy down to a respectable 20 or so kilometers, because really the main thing you want to worry about here now is that you could run out of, not only could you run out of fuel here doing this, and that's kind of the trick, but you can also do other things as well. You can burn up. So here I have another 3-second burn. I want to talk about what I'm doing here. We are burning retrograde, which means we are burning against the direction of our orbit. Now you could burn straight down, and you might eventually get down there, but there's a problem with that. It takes about 4 times as much energy. It also happens to increase your apoapsis when you do that. And we want to get down. Generally, you want a shallow trajectory coming back in rather than a steep one. So the way we can do that is we can burn retrograde, and that will allow us to move out of our orbit. So let's do that at about 1.5 seconds. By the way, to quick cut your throttle, you can hit X. Let's see how we did. We're at 19 meters per second. No, 20. And I am just going to turn on the, when we get in, I'm going to turn on the heat overlay. And one moment. Okay, we are back now. We want to re-enter this thing gracefully, so I'm going to turn on the heating diagram here. You can see we got a little bit of heat. But, that heat, as it turns out, is going to, it's going to be useful to us. Or maybe not useful to us, but it's not going to be that big of a deal. So, yeah, I'm just going to do the time warp real quick. We're coming in slowly, which is the way to come in. And if we maintain retrograde here, then we should be okay. Now, usually leaving this engine on when you re-enter can be a bad idea. But, And then you can see the speed at which we're coming in. We're coming in at orbital velocity, which is above 2.2 kilometers per second, or thereabout. And we just want to maintain our orbit. I'm going to do physical time acceleration here. Another thing too, the difference between the physical and on-rails acceleration is that on-rails acceleration, you can't control your vessel, but we can control it here. Now, when we begin heating up, well, first of all, we want to keep pointing towards our prograde vector, or our retrograde vector, so that this engine bears the brunt of the heating. I have fuel in it, so I'm going to keep it, but this can actually be a pretty bad idea, because the engines, in some ways, can't take as much heat. We know at least the capsule can survive, although depending on how energetic your landing is or your re-entry is, that can change. So we should begin getting the shock heating pretty soon. We're beginning to slow down. You can see our periapsis is slowly dropping into the planet. If we wanted to land here instead, what we could do is we could use our engine to slow down here. This is the desert west of Kerbin, so what we can do is we can use this engine to mitigate some of the heating issues here. We will heat up a little bit. And now that engine's spent, we are going to jettison it. And it'll move out of the way here. And we will heat up a little bit. You can see that we are beginning to get the shock heating going on, and that is making our vessel turn yellow. We don't want it to get too hot. And the reason we don't really want the we don't want to keep that engine on is that heat travels through the vessel. It propagates just like it does in real life. The important thing here is that we have you know, we're surviving. We've slowed ourselves up down rather, so that we will not heat up much. And before too long, shock heating will turn into Mach effects. Now you want to be somewhat careful with this, largely because of the fact that if you're not careful, then what may happen is that you may end up ripping off your parachutes, for instance. So I'm going to wait until after we get under Mach 1, which is going to be around 300 meters per second. It's even better to wait to deploy them until you're close by. Now, your altitude indicator here is relative to sea level. We just happen to be above the sea. So, if we turn off stability like that, we point in that direction because that's where most of our drag is. We're going to be pointing towards our prograde or retrograde marker. Re-entering towards your prograde marker is not such a nice thing. likely to burn up that way. But, we'll pull the chutes at a higher altitude now. I'm thinking maybe 1500. And there we go. Chutes are out. We are slowing down quite quickly. And we're landing pretty close to the surface here. You don't want your surface speed when you're landing to be above 6 as a general rule of thumb. That destroys most parts. Ideally, you want it to be as low as you're comfortable using it. But, you want it to be safe. There's a trade-off to make between parachutes and mass. So, we'll land this guy here, and we will recover it. And what that will mean for us is that we now happen to have, you know, we've successfully gotten into orbit, and if we go to the astronaut facility here, we can look at Jeb maybe. Well, I guess it won't track his rewards here, unfortunately. But, yeah, I mean, we gotten into orbit. That's a very simple thing to do once you're used to it. And with that having been said, next tutorial I believe I will cover satellites and orbital maneuvers, and we will deal with that later. But until then, this has been Thy Lord Root, and I will see you later.